Alrighty, so we're gonna start cardiovascular system today. Next week, you're gonna have metabolism exam, remember that. This is the recorded one. Okay, so let's chat about cardiovascular system. A few things. First, anatomy, as usual, only you have the list, you have the structures. It's entirely identification, okay? So you don't have to kind of, I don't want to go over all the blood vessels. You're going to learn chambers and cardiac chambers, okay? So what my plan for today is, I wanted to talk about blood flow through the heart, certain electrophysiology aspects of the cardiac muscle, EKG, cardiac cycle, a little bit maybe about cardiac output, but we'll see how it goes, okay? So the very first thing that I wanted to talk about to clarify, so it's kind of anatomical, but this question sometimes becomes a little complicated. The layers of the heart, that's the only sort of anatomy that I want to mention. So imagine that this is the pericardial cavity, okay, that's the cavity. Okay, good? And inside of that cavity is the heart. Okay, so that's heart. Now, there are certain layers that are associated with the heart. First of all, the outer layer that covers the heart on the outside is called visceral pericardium. So that's going to be, so I'm going to change the color. I'm going to use that. So that's visceral pericardium. Okay. Now, visceral pericardium is continuous with a pericardium pericardium that lines the walls of the cavity. Okay. Does that make sense so far? Now, the red line, I specifically make it represents the muscle of the heart, which we call a myocardium. Okay. And then on the inside, the heart is covered with a layer of simple squamous epithelium called endocardium. Are you with me? Endocardium. Now, oh, of course, endocardium. ENDOCARDIUM. So here's what we have. Look. The pericardium basically attaches the heart to the cavity. Okay, you follow me? And it kind of affixes it to the inside of that cavity. There's a fibrous layer here in the pericardium that anchors the heart. And what's important is that visceral and pericardium, they produce a watery fluid that fills that gap. You see the gap right here? See that gap that my finger is in? That's basically a cavity. So that cavity is filled with fluid, and that fluid prevents heart from being damaged. It's kind of lubricating. Okay? Now, in some cases, with some infections, say infection of a pericardium, it leads to inflammation and accumulation of fluid in that cavity. Now, imagine this. Imagine that you can see that lady to the left. You see the lady to the left out of this three, to the left? The heart is in the cavity. So imagine that the fluid around the heart starts to accumulate. Are you following? So your heart essentially becomes kind of squashed by that fluid. This is called cardiac tamponade, okay? And it's a result of pericarditis. I personally know a gentleman who suffered from pericarditis. The amount of fluid that they sucked out of the pericardial cavity was about 2 liters. 2 quarts, basically, okay? 2 quarts of fluid, that's a lot of fluid. So that's usually a result of infection. Myocardium can get infected, and that myocardium, infection of the muscle myocardium, causes problems with the cardiac contraction. One of the observations with the current coronavirus outbreak is that there are myocardial changes in people who suffer from that disease. So there are signs of infection. Endocardium can be infected. An infection of endocardium is called endocarditis. The most common cause are autoimmune diseases or bacterial infections. Usually it affects valves. We're going to talk about the valves. So far, you with me? Now, next thing that I want to chat about is the blood flow to the heart. So I'm going to draw a heart, and I strongly suggest that it's a really convenient way to kind of outline the blood flow, and it answers a lot of questions. If you can do it and you can explain it yourself, that is really helpful. Of course, I'm not going to draw a proper heart like this one. Okay, here's what I'm going to do. So this is a terrible color. This is the heart, okay? And as you know, it can be divided into 4 chambers, okay? Good so far? So since we are looking at the heart from that sort of perspective, so looking at my heart, the right side, left side, okay? And I'm going to show some of it in the models here, if I will be able to detach the cover, of course. Okay. So we've got 2 atria, right atrium, left atrium, and 2 ventricles. Right ventricle and left ventricle. Okay, we're good so far? Awesome. Now, atria are receiving chambers, ventricles are pumping chambers. Okay. So here's the blood flow. Right atrium receives the blood through superior vena cava and inferior vena cava. Okay. So let's do this. Superior vena cava. Vena cava. In this model, you can also kind of see it. So this here is inferior vena cava. Right, I'm going to step. Inferior vena cava. That one is superior. So blood flows from the tissues. So let's put tissues here. Now let me ask you this. The blood that flows from the tissues to the heart, does it have a high oxygen or low oxygen content? So that's blood from the tissues. Obviously, superior vena cava drains the blood from upper extremities in the head. Inferior vena cava drains the blood from everything below the head. Okay. So it gets into the right atrium. Then in the right atrium, from the right atrium, the blood enters right ventricle. Okay, through tricuspid valve. Okay. It enters into the right ventricle, and right ventricle pumps the blood into the pulmonary trunk and pulmonary arteries, so that's pulmonary swell. So that's pulmonary trunk, that's pulmonary valve. Okay, so we've got, I'm going to put some stuff here. PT is pulmonary trunk. Okay. And pulmonary valve. Okay, we're good so far? But this blood, this poorly oxygenated blood, will then go to the lungs. Okay? It goes to the lungs. Are you following this? It goes into the lungs. What happens to the blood in the lungs? Oxygenated, and it returns into the left atrium through pulmonary veins. Okay? From the left atrium, blood is pumped through the mitral valve, the left ventricle, and then from the left ventricle, it is pumped into the aorta and goes to the tissues. So that is the aorta. That's the aorta. So, oh, sure. Okay, we're good. So look at this, kind of, going over this one time like in the So deoxygenated blood returns from tissues and it enters the right atrium through the inferior and superior vena cava. Right atrium pumps the blood into the right ventricle through the tricuspid valve. Right ventricle pumps the blood through the pulmonary valve into the pulmonary trunk, which then branches into the pulmonary arteries. Pulmonary arteries carry the blood to the lungs, where it gets oxygenated, and from the lungs, it returns to the left atrium, it enters through the pulmonary veins. Left atrium pumps the blood through the mitral valve into the left ventricle. The left ventricle pumps the blood out through the aortic valve into the aorta. Blood gets delivered to tissues, and it all goes back. Okay? Good so far? Does that make sense? Okay, awesome. So a few things to mention, kind of short statements. First, you can see that not all arteries carry oxygenated blood. Pulmonary arteries carry deoxygenated, and not all veins carry blood that is low in oxygen. Pulmonary veins carry heavy oxygen from lungs. Does that make sense? The definition of a vein is a blood vessel that carries the blood to the heart, while artery carries the blood away from the heart. We good so far? We're good? Okay. One more thing. You can see that there are basically two sides of the heart. It's often, people say right side and left side. Does that make sense? So we usually associate the right side with what we call a pulmonary circulation. Look at this. So right side of the heart pumps the blood to the lungs. Are we clear? The left side of the heart is associated with what we call a systemic circulation, pumping to the tissues. Is that understood? Okay. So this is why we call it two circuits. Now I'm going to Well, I would love to have one of those boxes here, but it's too heavy and too risky to walk. But you can see the circulatory system models right there, Dr. Ashley. So let me ask you a couple of simple questions. The blood vessels that are associated with the lungs, you can see them extending to the left and right side from the heart. So circulatory blood vessels associated with the pulmonary circulation versus all the blood vessels associated with the systemic circulation. Which circuit is bigger size-wise, pulmonary or systemic? Systemic. Now, a really provocative question. Which circuit has a higher blood volume? Same. The circuits have the same blood volume. Pulmonary circuit and systemic circuit, they have the same volume of blood at any given moment. I know that it sounds really unrealistic, doesn't it? Because pulmonary circuit is so much smaller, right? But here's an example. So we here at Lakeland, okay, imagine a campus. Now Katie's in the car, I'm in the car. And we are given two tasks. Katie is given a task to drive around Lakeland campus in 10 minutes and come back to the same spot in 10 minutes, right? I'm given a task to do basically also drive and come back to the same spot in 10 minutes. My route is 306 Manor Avenue, 615 I-90. So my route is much bigger. Does that make sense? Can we both make it in 10 minutes? Well, she definitely can. I probably can if it's 1 a.m. in the morning and there's no police around, right? The point is, we both will complete the circuit, but I will have to drive much faster. Does that make sense? So in order to circulate equal volumes of blood for both circuits, think of it this way. The flow through the pulmonary circuit is relatively slow. Like the pace of blood going through the vessels, like how many millimeters per second. You see what I'm saying? But the pace of blood through the systemic circuit is much faster in order to complete the circuit in the same amount of time. Does that make sense? I deliberately don't use the term blood flow because the definition of blood flow is volume per minute. Do you understand? And blood flow for both circuits is the same. So both circuits, you have 5 liters of blood pumped in 1 minute. But blood moves much slower through the pulmonary and much faster through the systemic. Does that make sense? That also explains the fundamental difference between these two circuits. Pulmonary circuit has very low resistance and very low pressure. Do I make sense? Systemic circuit has high resistance and high pressure. The difference is about 4 times. Does that make sense? You know, because blood doesn't have to, because it doesn't move that fast. The resistance, the higher the velocity, the higher the resistance. Good? That will come back. We're going to discuss it today, hopefully. That fundamental thing, that blood flow, the volume of blood in both circuits is the same. Okay, we clear? Now, I wanted to kind of highlight quickly through the heart run through. So we've got Vena Cava, getting the blood into the right atrium, then through the tricuspid valve into the right ventricle, from right ventricle into the pulmonary trunk, from pulmonary trunk through the pulmonary arteries to the lungs. From the lungs, blood returns to the pulmonary veins into the left atrium, from left atrium through mitral valve into the left ventricle, from the left ventricle pumps into the aorta. Good. Any questions on this one? Okay. Little note that I'm going to put it on the screen. So these valves are called atrioventricular because they are between the atrium and the ventricle. Because I see more. Okay, semilunar, because they shaped each sort of, what's that proper word? Each flap of the valve is shaped like, sorry, shaped like this. So this is how it closes, this is how it opens. Does that make sense? When there's pressure, opens. That's another important thing that, yeah, we'll wait till cardiac stop. So far, we're good? Okay, now we're going to switch gears. Can I cue this whole thing? Now we're going to switch gears. We're going to talk about a little bit about cardiac muscle. We segue into the EKG. So cardiac muscle okay, good. Cardiac muscle is involuntarily controlled. Okay, branched, and we talk about one branched. I say uninucleated with an asterisk. Sometimes it can be two nuclei, okay, but rarely. There are intercalated discs connecting cells, the gap junctions, and it's triangular. That is really, which means it consists of sarcomeres. Now, I want to ask an embarrassing question, which may not be embarrassing after all. Do you remember what sarcomeres are? No. Okay, fair enough. So kind of a crash course in the mechanism of muscle contraction. Muscles, all muscles, contract by sliding filaments mechanism. So you've got, look at me. You've got, this is going to be a thick filament, myosin. This is going to be a thin filament, actin, okay? They slide against each other. That's it. Okay? So sarcomeres are elementary units that, when contract, they shorten. Okay? So basically, actin filaments, they slide to the center of the sarcomere. We're good? That clear? Okay. This is, so sarcomeres explain why it's striated. I have some stuff in the lecture notes that we'll focus on. Why branched? Why is branching important? When you think about the skeletal muscle always contracts in a single direction. Do you understand what I'm saying? So for instance, when I extend my elbow, triceps contracts and pulling on ulna in one direction. Does that make sense? When I abduct my arm, the deltoid muscle pulls unidirectionally on the humerus. Good? In case of heart, it has to contract in 3 dimensions. Does that make sense? Okay? This is why branching is important, to create this three-dimensional contractile structure. Right? Good. Now, last little bit, again, as a reminder for the mechanism of contraction, to make sure that you're well covered for the exam. What is the difference between the contraction of a skeletal muscle and the cardiac muscle? So for this, we're going to draw the curve with depolarization, repolarization, and stuff like that for the cardiac muscle. I want to remind you that involuntary contraction means that cardiac contraction can be stimulated not only by the nerve signal, by hormones, by chemicals, even by mechanical stimulation. Okay, we're good? So here's the deal. So that's millivolts, that's time, and that's the resting membrane potential for the cardiac muscle, okay? So when cardiac muscle gets excited, the cardiomyocyte, the cell gets excited. The first thing, it opens sodium channels, okay? And when sodium channels are opened, sodium, in which direction does it flow? Does the sodium diffuse into the cell or out of the cell? It's kind of backed question a little bit. You have to think about, did we talk about 4 ions that you must know? Did I mention 4 ions? Okay. So 4 ions, the concentrations that you must know, and I'm not talking about numbers, okay? It's not about numbers. So the concentrations higher outside of the cell, sodium, calcium, fluoride. Okay? The concentration higher inside of the cell, potassium. Know this. Just absolutely know this. We clear? So now I'm going to ask this question again. When sodium channels open, sodium, where does it diffuse? Bingo. Diffuses inside of the cell. It is positively charged. Okay? Sodium is positively charged. So diffusion of sodium will make a membrane potential of a cell more positive. Does that make sense? Okay? Are you following me here? Okay? So that first step is depolarization. Sodium flows in to the voltage gated via voltage gated channels. Okay, so depolarization, sodium flows into the cell, diffuses into the cell via voltage gated channels. When cell is completely depolarized, sodium channels close, and we'll talk about that closure. And channels that are open are potassium and calcium channels. Now, let me ask you this. When calcium channels open, where does calcium flow? Diffuses. Where does calcium diffuse? And potassium? Outside. But the calcium charge is higher. So for some time it compensates for potassium efflux. So basically this plateau is due to influx of potassium. In all cases here, I'm not going to write it anymore. It's going to be voltage gated channels. We good? Okay. Finally, look at this. At this point, calcium channels close. And the only one that is left open are potassium channels. Are you with me? So potassium starts to rapidly leave the cell. That leads to repolarization. Are we clear? Does that make sense? Okay, so here's the deal. You do need to know what happens at each stage. Let me go over it again. So in the beginning of the contraction, cardiomyocyte is depolarized because of the influx of sodium. Okay? At the peak of depolarization, sodium channels close, calcium and potassium channels open. Calcium flows in, potassium is out, but calcium flow basically maintains the plateau. That plateau corresponds with an extended contraction. Right? Now then, calcium channels close, potassium channels remain open, cell repolarizes, ready to contract again. Why plateau? If you will compare it to skeletal muscle, skeletal muscle contraction is pretty much instantaneous. Does that make sense? It depolarizes and repolarizes immediately. Skeletal muscle, when classically the muscle twitch, the contraction of a single skeletal muscle fiber will go up and down. It's not a sustained contraction. In case of cardiomyocyte, it is a sustained contraction. Does that make sense to you? So this plateau ensures that cardiac muscle cell stays contracted for an extended period of time, allowing to squeeze the blood out. Are we good? Right? A couple of really, really important things. Well, you may remember we talked about it when we spoke in regards to neurons and mostly neurons, so-called absolute refractory period. Maybe it rings the bell, maybe not. Here's the thing. When sodium channels close here, they aren't just closed, they're inhibited, which means you can't open them for some time. That makes sense? Because what if they wouldn't be inhibited? Now imagine they close here, you have a contraction of a skeletal muscle, and suddenly another stimulus arrives. Sodium channels open again, and you just keep maintaining that contraction, which means that your heart will start squeezing and will never relax. It will go basically into tetanic contraction, which is not good. Does that make sense? So this absolute refractory period when you cannot possibly stimulate another contraction of the cardiomyocyte, ensures that there's no continuous tetanic contraction. Sure, your heart can beat really, really fast, but it will not produce just one long contraction. Does that make sense? Good? Any questions? Okay. So this is another great example of if you can draw it, you're fine. You can draw and explain what's going on. I'm going to go on a small tangent here. I mentioned a couple of times before the approach of brain dump during the exam. Remember? When you just take a piece of paper and just put the stuff that you know on that piece of paper. This is a great opportunity for a brain dump. Like before you start answering questions, just take a scratch paper, put this, put blood flow through the heart, cardiac cycle, intrinsic conduction system, all that kind of stuff, okay, on the paper. Because then you have a question, just look back at your drawings. Okay, given that they're correct, you're gonna, it becomes very easy to answer. Any question? And I encourage that. Okay. Moving on. Now, if you think about the whole idea of cardiac contraction, having some center in the brain or in the spinal cord or in the brainstem that would constantly send signals for the heart to contract sounds like a lot of work. And on top of that, what if you become unconscious? So heart can contract by itself without any external stimulus. Am I clear? This is possible because of cells that are known as pacemakers. And these pacemaker cells, they're slightly different outline of depolarization process. Okay. So this is a threshold for firing, threshold for generating an action potential. So in a typical pacemaker cell, the contraction starts with a pacemaker potential. Which is due to the slow, I'm going to put it just sodium influx through the leaky channels. Okay, you have leaky channels, look at this. And the sodium just slowly creeps in. Does that make sense? Okay, cell slowly approaches the threshold of activation. Got it? Good. Blink once. Good. Good. Now, next thing, look. When it hits the threshold, voltage-gated calcium channels open, and calcium depolarizes the cell. Voltage-gated calcium channels. Good? Okay, and finally, calcium channels closed, potassium channels open. Okay? What happens here? Potassium channels closed, and so in the pacemaker cell, look at this. Starts with the leaky sodium channels that allow the cell to approach the threshold. Then it depolarizes due to the opening of calcium channels and influx of calcium. And then potassium efflux repolarizes the cell, and then potassium channels close. Sodium again creeps up, brings it to yet another depolarization threshold, and so on and so forth. Good. So this process does not require any external input. From sort of kind of observable standpoint, do you see Indiana Jones and Temple of Doom? There's a I wasn't too enthused about the movie, but there's an episode, an evil guy rips out the heart from a person. He holds the heart like this. The heart keeps on beating. That's physiologically correct. Sometime it will be contracted. It does not need any input from any nerves to do so. Does that make sense? As long as there's ATP, as long as there's calcium, as long as everything is fine, you can make, like, you can isolate a heart and provide all necessary nutrients and stuff. Sure, it'll work. Good? Any questions? Okay. So which brings us to the discussion of the intrinsic conducting system of the heart. Now, I use the words intrinsic and extrinsic. So what do they mean? Intrinsic in physiology refers to the organ. It refers to local homeostasis, the homeostasis at the organ level. Does that make sense? Extrinsic refers to the body, the organism, and refers to the homeostasis at the level of an organism. So, intrinsic conduction system of the heart maintains heart rate, makes sure that contractions are rhythmic. Are we clear? Extrinsic controls regulate the heart rate based on the needs. When you exercise or not, excited, so on and so forth. Are you following me here? That's the basic. So let's start. Sorry. Okay, so that's heart. That's right atrium, left atrium, right atrium. There's not going to be a lot of anatomy control in here. The conduction system, I think you should think of it as electrical wiring of the heart. Does that make sense? The whole conduction system consists of pacemaker cells that we just discussed. These pacemaker cells are organized in the nodes and bundles and fibers, okay? So it all starts in the right atrium of the SA node. So it would be, I'd say somewhere about here, the SA node, okay? And SA node sends the signal, generates that depolarization wave that spreads across the atrium. Now, how can change in the membrane potential spread through the layer of cells? Now, that's a hard question. You may not remember that. How can change in the membrane potential spread through the layer of cells? Any ideas? I'll give you a hint. Cells are connected by some kind of a junction. Perfect. Yes, they gap junctions. So if this is the cell and the hallway is the cell, and the door is a gap junction, imagine that there's just an opening, right? If membrane potential changes here, this change in the ion concentration will immediately be reflected by the change in the ion concentration across the gap junction. Does that make sense? So this gap junction connections between the cells of atria allows when SA node depolarizes, the entire atrium depolarizes. Am I clear? Which means entire atrium contracts. Now here, right here, is another node, which is AV node. So SA stands for sinoatrial, while AV stands for atrioventricular node. That makes sense? Now from here, signal enters a bundle of His or atrioventricular bundle, and then splits into two branches. And these branches eventually spread into the Purkinje fibers. Okay? So atrioventricular bundle, Purkinje fibers. So far, are you kind of full? So look what happens in terms of the signal. So signal depolarization wave spreads through the atrium. It reaches AV node, just, as any other corner of atrium. Goes along the atrioventricular bundle and into the branches and into the Purkinje fibers, reaching ventricles. Does that make sense? So one more time. SA node generates the signal electrical depolarization wave travels through the atrium, reaches AV node, then enters the atrioventricular bundle, spreads through the bundle into the Purkinje. Make sense? You're not finding anything strange here? It is right, pictures, just something really, really strange. No? Well, let me ask you this. It's more of a rhetorical question, but here's the question. Why signal can spread through the atria from SA node, but it doesn't spread into the ventricles? You see, like, why didn't I put that SA node, that depolarization wave just swept through the entire body? Why? So again? Let me guide. I love this, when we kind of go step by step together. So what allows the spread of the signal, as Katie mentioned, what allows the spread of the signal through the atrium? Gap junction. This is really a simple question. Don't overthink it, just from common sense. If signal does not go from atria to ventricles, except through AV node, what does that mean? Bingo. Atria and ventricles are not connected by gap junctions at all. Does that make sense? That's really, really important. The only electrical connection between atria and ventricles is AV node. Make sense? So this explains one really important thing. If you think about cardiac contraction, look at my hands. So this is atrium and this is ventricle. Atrium contracts first and ventricle contracts second. You see what I'm saying? Why? Because the signal from SA node will be delayed at AV. It's kind of tiny. It's like, have you ever been to Blossom Music Center? Okay, have you ever been to a concert? You have a crowd and the crowd goes through the gates and there's always going to be a traffic, a jam at the gates because you try to squeeze a massive number of people through 3 doors, right? That's what happens here. That's a delay. That allows atrial contraction and then ventricular contraction. We good? Well, and then, it goes through the branches. Yeah. Okay? We're good so far. So now, let's take a look at some other interesting, really, really interesting features of these nodes. So first of all, since each node consists of pacemaker cells, each node sends signals with a certain frequency. In a healthy individual, SA node is a pacemaker. It sets the rhythm, okay? Now, if you take what's called an intrinsic rhythm for SA node, it is 100 to 120 beats per minute, okay? Some of you it may seem suspicious, but we'll get back to it. Okay? Now, what about AV node? For AV node, it's 50 to 60 beats per minute. So imagine, hypothetically, listen, hypothetically, Your SA node is dead, myocardial infarction. Okay? So what happens in this case? AV node takes over. When you have a heart rate of 50 to 60 beats per minute, are you going to feel well? Not really. It's too slow. Will it still be alive? Yes. But it's going to be pretty slow. If AV node doesn't work, then bundle and Purkinje fibers will take over, and they intrinsic rate is 30 to 40 beats per minute. Is it survivable in the long term? It is not. This is why you need a pacemaker. Give that. We'll get back to this. So far, does that make sense? Now, nobody noticed, but let me ask you this. If SA node is the node that sets your heart rate, what is your heart rate? Seriously? You think so? I'm trying to find mine. So I'm looking at as good as it does. Mine is 66 now. And I feel fine. Like I'm not dying. I don't need a pacemaker. So why is my heart rate? Why is your heart rate is actually between 60 and 70 beats per minute? So, good idea. No. Something is slowing your heart down. Does that make sense? Now, remember autonomic nervous system? Which part of autonomic nervous system will be responsible for slowing down the heart? Parasympathetic. Rest and digest. So what essentially happens? Now look at this. You have a heart, okay? You have a cardiac center in the medulla oblongata, okay? And in the medulla, you have cardio acceleratory center. That's a long word. And cardio inhibitory. Does that make sense to you? It's all parts of medulla. So cardio inhibitory center, it slows the heart down. Cardio acceleratory center stimulates the heart rate. Are you with me? Here's the thing. This is a tug of war, right? They kind of, whoever wins, the heart is going to either slow down or speed up. At rest, cardio inhibitory, parasympathetic center, winning. When you need to, when you start exercising, the parasympathetic stimulation naturally goes away. So heart starts to beat faster. And then sympathetic stimulation kicks in and it beats faster and faster and faster. Does that make sense to you? Are we clear? Good, good. Trying to think what I forgot. Here we go. This, why, so, no, yeah, I think kind of regarding the intrinsic conduction system, we covered it pretty well. So I'm going to give you one really fun story. So normally, right, medulla oblongata kind of slows down the heart. Right? How does the signal from medulla is delivered to the heart? Through what? Huh? Say again? Nerves? Neurons, yeah. Bunches of neurons which are nerves. Yeah, neurons. You're right. Perfect. Yes. So there's a nerve, right? You may even remember the name. What is the biggest nerve, cranial nerve, that controls virtually all the organs of abdomen, thoracic cage. Cranial nerve 10, like a big ass important nerve. That's the vagus. Yes, the vagus nerve that controls the heart. We good so far? Here's the actual case that happened in the hospital. There's a patient who underwent heart transplant surgery. And the patient is resting in the room. The nurse is checking up on the patient. And what the nurse realizes is that, holy crap, the patient's heart rate is 120. Heart transplant yesterday, the person is still, drugged under 20 BPM. And the nurse comes over to a physician and says, holy cow, we have a patient on transplant. It's like 120 BPM. What are you going to do? He's going to die. And the physician says, no, it's fine. But you don't understand, says the nurse. It's 120 BPM. It's okay. No, you don't get it. It's 120. Yeah, I know. It's fine. That's what it's supposed to be. Now let me ask you this. One, it is what it's supposed to be. No? Well, before you put a new part in, what do you have to do? Take out the old one. Now, how are you going to cut out the old one? What you going to cut? And also what? A vagus nerve, right? So basically, yeah, you quite literally, you cut all the connections, including nerve, and you put the new heart in. Can you stitch aorta? Sure. Can you stitch Vena Cava? Yes, it's all doable. I mean, I actually saw cardiothoracic surgeons sitting in the atrium of the medical center just practicing. It's insane. Like they like seamstresses, just not looking, just practicing stitching. Okay, but nerve you can't stitch. Essentially, perform a local lobectomy, and from now on, SA node takes over, and it's just new normal. Does that make sense? You got it? Okay. You know what we're going to do? How are you feeling about some EKG? We're going to quickly go over what electrocardiogram is and the main parts here. So you can, and look, I'm not a cardiologist, of course. I'm not an EKG technician. So I kind of know physiology behind. That's what I ask you. So EKG, you take a machine and you measure an electrical activity, basically voltage in the heart. Okay, and depending on where your detector is, where your lead is, EKG may look slightly different, which is fine. Sort of a generic EKG profile of a single heartbeat will be this. Look. First, you have depolarization of atrium. Does that make sense? Okay, that's called P wave. Then eventually, the signal will go through the node, through the atrioventricular bundle. It will start depolarizing ventricles. Now, interestingly enough, look, when ventricles get depolarized, atria get repolarized. So these two events, repolarization of atria and depolarization of ventricles, they overlap. That's it's a flaccid QRS complex. Okay, so this is going to be QRS complex. Okay, QRS. Okay. okay? And next, finally, when your ventricles repolarize and relax, that's the T. Okay? So this is the atrial depolarization. This is the atrial repolarization, ventricular depolarization, okay? And this is the ventricular repolarization. Good? Now, there are some interesting elements, for instance, PR interval. Why it's important? Because P is the start of atrial depolarization, and R is the start of ventricular depolarization. It basically tells you how much time it takes for the signal to go from here to here. What is the time between your atria starting to contract and your ventricles starting to contract? Does that make sense? Another ST segment here shows you for how long your ventricles are fully depolarized and are contracted. Does that make sense? Now, why do we care? We can detect certain abnormalities in the heart using EKG. And this is what I want to kind of talk to you about. It's really fun to chat. So first of all, have you done EKG in your life? I mean, you just lay down, they put leads on you, and then you have like a fence of impulses, right? Now, first of all, EKG will detect the frequency of heartbeats. Right? Now, you probably heard terms tachycardia and bradycardia. Tachycardia is the high heart rate, bradycardia is the low heart rate. So tachycardia would be around 100 and above, and bradycardia would be 40 and above. Are those numbers bad? Intrinsic? No. They just show how fast. For instance, if I will be, I don't know, running right now, I will be tachycardic. Does that make sense? If you will take Michael Phelps and measure his heart rate when he sleeps, he's probably going to be bradycardic because he's a trained athlete. Does that make sense? It just relates to higher or lower heart rate. Now, what's interesting is to chat about some abnormalities on EKG associated with the defects in the intrinsic conduction system. So let's start with this. What if your SA node is not there? Which element of EKG you're not going to see? Yes, P wave is gone. Are you going to have PRSNT? Sure, of course you're going to have them. Does that make sense? Because, because SA node doesn't work, but AV does. It will take over. Good? This is called SA block. Now, what if you have a problem with AV node? Now, remember my comparison of AV node with the doors into, say, a concert hall? So now, what can be a problem with the doors? Problem number one is that instead of 6 doors, you have 2. Okay? How is it going to affect? So your AV node is electrically narrow. How is it going to affect the rate of electrical transmission from atrium to ventricle? So signal has to go through AV node to reach ventricles. Does that make sense? If AV node it's too narrow, how is it going to affect the time that it takes for the signal? slow down. Now, what reflects that time on EKG? PR interval. So if you have a problem with AV node, PR interval will be extended. Does that make sense? This is called AV block, grade 1 AV. That make sense? Now, what if your doors into the concert hall are randomly closing and opening? Sometimes they close, sometimes they open. So your AV node, sometimes it allows the signal to go through, and sometimes it doesn't. When it doesn't let the signal go through, what you're going to lose? Q, R, S, and T. Does that make sense? You're going to have atrial depolarization, and that's it. That makes sense? So this is called second degree AV block. And finally, third degree, you can imagine, is when AV node is impenetrable for the electrical signal. Does that make sense? In this case, your EKG is going to look completely different because you're going to have an overlap of P wave and whatever rhythm your Purkinje fibers and atrioventricular bundle will form. Does that make sense? This is called the third degree AV block, and it requires pacemaker for sure. Does that make sense? Now, if you're wondering what can cause those blocks, myocardial infarction. We never mentioned it, but your heart has its own blood supply. You see those blood vessels here? Those are coronary vessels. Okay? The coronary arteries here and here, they start from aorta. Okay, so they technically are part of systemic circulation, right? They start from aorta. And then they supply blood to the heart. If a clot, a thrombus, occludes one of those coronary vessels, it prevents the blood flow to a part of the heart. This part becomes ischemic, and cells start to die. Do I make sense? If it's, I don't know, if it's just a part of a muscle, it doesn't contract anymore. But if the vessel that supplies blood to the area with SA node is blocked, then cells that comprise SA node can die as well, and SA nodes die, right? Or AV nodes die. Am I clear? Now, these were pretty bad conditions. Now, I want to switch a little bit, to something more regular and explain the concept of ectopic focus. So what is ectopic focus? Ectopic means out of place. This happens when stimulus originates not in SA node, but someplace else in the atrium. Does that make sense? Can be easily precipitated by coffee or nicotine or any other stimulant. Totally normal in a healthy adult. It's almost guaranteed that if you will take EKG long enough in a person, you will find ectopic focus. Does that make sense? Now, ectopic focus can happen in the atria or it can happen in the ventricle. Ventricular ectopic focus is worse because, first of all, it can mess up the normal transmission because it can go back. Okay? So it may mess up the synchronized contraction of the ventricle. Basically, it increases the risk for ventricular fibrillation. That makes sense. So this brings us to the concept of fibrillation. There's an atrial fibrillation and ventricular fibrillation. So atrial fibrillation is when cardiomyocytes in the atrium do not contract in a synchronized manner, but start to contract whenever they want. Does that make sense? So your atrium, instead of doing this, okay, starts to do something like this, it doesn't pump anymore. Is it a, how to say, is it a question of life and death? Atrial fibrillation. It's not, because atrium doesn't really pump that much. Does that make sense? So if atrium fibrillates and atrium fails to pump whether left or right, it's not great. The cardiac output, the pumping capacity will be impaired, but people live with atrial fibrillation. Good? One of the main risks associated with it actually is clot formation. Clot may be formed in the heart and then end up in the coronary vessels or cerebral vessel, of course, myocardial infarction, stroke. Does that make sense? Now, if ventricular fibrillation occurs, then it's bad. Because if ventricles start to do something like that in asynchronized manner, can they pump? They can't pump, blood isn't getting delivered to the lungs and to the tissues. Does that make sense? So, in case of ventricular fibrillation, or as some, you probably saw in the doctor shows TV vision, what people do? How do you fix ventricular fibrillation in a patient? What do you do? Huh? How do you fix it? Using what? AED. Yes. Yes. Electrical defibrillator. Make sense? So you basically run an electricity through a person. What do you think it does? Again? No. It's actually much more interesting. And that's perfectly fine because that's common. Like people think that it restarts the heart. It doesn't. I call it a lunch lady at the third grade lunchroom. Have you ever been to a third grade lunch? It's a noise. It's a constant noise. You cannot understand what they like. They constantly yelling and screaming at each other, right? And talking to them is no use. So in order to get them to order, there's a lunch lady who will yell, silence, and kids will freeze in their tracks, right? So this is what AED does. The electricity, it wipes out all electrical impulses in the heart, completely obliterates them. It stops them. Does that make sense? Completely stops. And then, if it manages to start over, it's like a reset button on a computer. If it manages to start over, good for patient. If it doesn't, it doesn't. Okay? You watch movies, actually, there was a study of what's the frequency of people, being brought back to life, the result of cardiac resuscitation procedure in the movie. 70 to 80% of movie patients are resuscitated. The real life percentage, any guesses? Huh? You are optimistic. You are optimistic. Why? About 5% patients with ventricular fibrillation actually can be successfully resuscitated, which is a pretty dark picture. If you think like from a standpoint of EMT specialist or ER doctor or anyone who has to deal with it, basically you walk into that situation with 95% chances that that's it. Okay, that makes sense? Questions about, so the concepts that we discussed, ectopic focus, AV block, SA block, atrial and ventricular fibrillation, I can ask you about whenever we talk. Okay. So we're going to take a break. When we'll come back, we're going to talk about cardiac side, but that's Let me pause it. So, kind of, I'm going to ask you definitions. Cardiac cycle describes virtually all the processes in the heart during a single heartbeat. Does that make sense? So we will describe sort of, flow of the blood, opening and closing of valves, electrical changes, depolarization, repolarization, stuff like that, during a single heartbeat. Are we clear? Okay. So I'm gonna make an attempt to draw this step by step and actually tricuspid valve between the right atrium and right ventricle. It only allows blood flow to get from atrium to ventricle. Does that make sense? Like this door, you can only open that way. You can't open it back. Are we clear? So pressures will become absolutely critical when we talk about the cardiac cycle. So we're going to start. Oh yeah, and another important thing about cardiac cycle. Whatever happens on the left side and right side of the heart happens at the same time during the cardiac cycle. Do I make sense? So when I say atrium contracts, it can be left or right atrium. Are we clear? Since systemic circuit is kind of more important, I would say, we're going to focus on the events in the systemic circuit. Am I clear? That makes sense. So I'm basically going to be talking about left atrium and left ventricle. You can keep in mind that whatever happens on the right side is the same, just, instead of mitral valve, it's going to be tricuspid. Instead of aortic valve, it's going to be pulmonary. Okay, good? So the first stage of a cycle, which sounds completely oxymoronic because it's a cycle, but the first step is diastole. Which means everything is relaxed. Okay, so we've got atrium and ventricle, right? Left side. Okay, so blood flows freely into the atrium through the pulmonary veins, and then from the atrium through the mitral valve into the ventricle. Does that make sense? Now, since it's a left side, we have aorta that is separated by the aortic valve, right? Now, at this point, the aortic valve is closed. Let me ask you this. This aortic valve, closed aortic valve, why is it closed? Remember our door example. Pressure, because pressure in the aorta is higher than the pressure in the ventricle. Now, mitral valve here is open wide. Yeah, because atrial pressure is higher than the ventricular. Does that make sense? So here's what we can write down. We can write down that pressure in the atrium is higher than the pressure in the ventricle, while pressure in the aorta is also higher than the pressure in the ventricle. Does that make sense? So heart is completely relaxed. Okay, blood freely flows into the ventricle, filling it up. This is called ventricular filling. Does that make sense? Since there is no contraction, is there any electrical activity right now? No, there's no contraction. Basically, it's a flat line on EKG. So we good? Now, next, as I mentioned before, the first chamber that starts contracting is atrium. So we go into the atrial system. Just pretty straightforward. Okay, same story. Atrium, ventricle, valve is open. Okay, valve is closed. Now, look. Atrium contracts. Can you see that? Which pushes the blood, last bits of blood, into the ventricle. Does that make sense? We're good? What I compare it to, did you ever see videos from Tokyo subway? No? In Tokyo subway, there's a special profession. There are people that squeeze people into the cars, the train. Like it's so packed that they're special. I'm not kidding. I'm not making it up. So they will push people to stuff them into a car or a train. You know, it's really that. Does that make sense? So when blood flows freely, that's people walking into the train by themselves. When atrium contracts, that's those Japanese folks pushing passengers into the train, stuffing them in. Does that make sense? Last real small bit. Are we clear? So I want to focus your attention that during atrial system, ventricle is still relaxed. Okay? So it's still in diastole, and the amount of blood that you can find in the ventricle at the very end of ventricular diastole is called end diastolic volume. Now, pressure relationships remain the same. Okay, ventricular pressure is the lowest. But do we have any contraction going on? Do we have electrical activity going on? Anyway. Good. Okay. Next. At this point, ventricle starts to contract. And that's going to be sort of an overarching. I'm going to put ventricular system. So there's going to be two events under. So event number one under the ventricular system is this. So ventricle starts to contract. Okay? There's blood in the ventricle. Okay? Are you following me so far? And as ventricle contracts, what happens to the pressure inside of the ventricle? Huh? That's ventricle. It starts to contract. What happens to the pressure inside of the ventricle? It increases. So ventricular pressure becomes higher than the atrial pressure. Does that make sense? Now remember our door exercise? So ventricle is right there, in the Holy. Atrium is here. When ventricular pressure becomes higher than the atrial, what happens to the valve? Yes. So the pressure becomes in the ventricle. The pressure in the ventricle. I was the ventricular pressure. Okay, Katie was atrial. Okay, I become higher than atrial pressure, so atrial pressure cannot open the door. Does that make sense? Valve closed. But it's not high enough to be more than the pressure in the aorta. So this valve is closed as well. Does that make sense? So aortic pressure is still higher than the ventricular pressure. Okay, we good? Now, look at this. Are any valves open? Can any blood get into the heart in the ventricle? No. So the volume of the blood will not change. Does that make sense? This is called isovolumetric contraction. Are we clear? Isovolumetric means same volume. From the lungs? It probably is, but it cannot flow because at this point the pressure in the atrium is just so much lower. And you actually asked a really good question, because what we do with a cycle, we break it into steps, and we represent it like at this moment this happens, at this moment this happens, and at this moment this happens. But it's not really true because it's a continuous process. Make sense? We kind of disregard any flow, which for sure happens. Good? So far, are you with me? So this is isovolumetric contraction. Pressure in the ventricle keeps on rising until it becomes higher than both atrial pressure and aortic pressure. Now let me ask you this. When ventricular pressure is higher than atrial pressure, in which position is mitral valve? Yes. When ventricular pressure is higher than aortic, in which position the aortic valve? Open. Does that make sense? So blood is being pumped into the aorta from the ventricle. Does that make sense? That's the ejection phase. We good so far? Okay, now look at this. Look at this. As blood is being pumped into the aorta, so you stuff more and more blood into the aorta. The pressure in the aorta, with all that incoming blood, will start to go up. So aortic pressure rises, and at some point, look what happens. You have aortic pressure higher than ventricular, but ventricular pressure is still higher than the atrial. Didn't we see it already? These pressure relationships. Did we see them already? Which stage? Isovolumetric contraction. This time what happens, not only all that blood is sitting in the aorta, ventricle starts to relax. Does that make sense? So if this is the case, if ventricular pressure in between the aortic and atrial, what's going to happen to those valves? So again, they both closed. Yes, very good. They both closed. Okay? Are you following me? Let me ask you this. When blood from the ventricle is pumped into the circulation, it's kind of, wink question, but all of the blood is pumped out? No. No, some is left. Okay? So there is some blood left at the end of ventricular system. Does that make sense? Here's the blood left at the end of the ventricular system. This is called end systolic volume. Now, here, look at this situation. Both valves are closed. Can any blood get into the ventricle? No. Ventricle is relaxing. Therefore, it is called isovolumetric relaxation. Does that make sense? We clear? So, in terms of EKG, this will be QRS complex, and that's T1. Okay? Are you following? Let me go over this stuff again. So we're going to try, and if you don't mind going back and forth, we're going to try it like in a reasonable manner. Dialogue. So in diastole, heart is fully relaxed, right? Blood flows freely into the atrium through the open mitral valve into the ventricle. The pressure in the ventricle is the lowest, slightly lower than atrium, and very much lower than aortic. This is why aortic valves. Okay. Then atrium depolarizes, which leads to contraction, speed. Atrium contracts and squeezes last little bits of blood into the ventricle. Ventricle is still relaxed, it's still in diastole, and at this point, it accumulates as much blood as it can. It cannot get any more than that. Does that make sense? At the very end of diastole, that's the maximum amount of blood in the ventricle and diastolic blood. Ventricular walls are depolarized. Okay? So ventricle starts to contract, and rising pressure in the ventricle closes the mitral valve, tricuspid valve. Okay? But the pressure is not yet higher than the one in aorta. So ventricle is in between the atrial pressure and aortic pressure. Therefore, all valves are closed. Okay? Volume of the blood in the ventricle does not change. So we're looking at isovolumetric contraction situation. Same volume. Eventually, ventricular pressure becomes higher than both aortic and atrial, which keeps mitral valve closed, but aortic valve opens. And contraction of the ventricle. Contraction of the ventricle pushes the blood out through the aortic valve into the aorta. We're good? Now, increased pressure in the aorta and simultaneous start of relaxation of the ventricle, so T-wave, flips the pressure relationships. So ventricular pressure is lower than the aortic. It's still higher than atrial. So that amount of blood that was left in the ventricle after the contraction, so-called end systolic volume, remains the same during isovolumetric relaxation. Does that make sense? Once the ventricle is completely relaxed, we get back to diastole. The ventricular pressure is the lowest. Atrial is slightly higher, so mitral valve opens, aortic valve is still closed, blood again freely flows into the ventricle. Does that make sense? So that's one cardiac cycle. Are we good? Okay, so a few notes here. First, what produces cardiac sounds? Closure of the valves. Okay. When flaps come together, that's the sound. Are we clear? Second, why do we listen to the heart? Well, we physicians. For instance, imagine that the valve is not closed completely. Okay? See the door? Imagine that the blood is supposed to go that way, and then pressure rises in that chamber down there in the hole. The valve doesn't completely close back. So what's going to happen? Imagine that mitral valve here is not completely closed. When the chamber will start to pump the blood out, what's going to happen? Backflow. It's called regurgitation. You can hear the regurgitation, and that means that the valve is dysfunctional. That puts extra stress on it. That make sense? I mean, I told you before, this is all about pumps. So imagine that you are pumping bicycle tire, but your pump sucks and leaks air. You're going to spend much more time and effort to pump the tire. Does that make sense? So your heart has to kind of, pump harder to comply with the requirements of the body. Does that make sense? Now, a couple more things that I wanted to discuss here, and I really wanted to keep it on the board. So if you don't mind, I'm going to be writing kind of somewhere here. Can you all see more or less? So everything that you need to answer my questions that I'm going to be asking now is on the whiteboard. I guarantee that. So look at what's written here and tell me. So there is a concept known as stroke volume. So stroke volume is the amount of blood that heart pumps with each heartbeat. Does it make sense to you? Are we good? Amount of blood that heart pumps with each heartbeat. Good? Look at the board and tell me what is the sort of mathematical equation to express stroke volume. What is stroke volume? Everything is written there. How would you calculate stroke volume? Any ideas? No? Okay, I'm going to give you a hint. I went to buy potatoes. I had $10 in my pocket. And I bought potatoes. I had $4 in my pocket left. What's the price of potatoes? So everything that you need to tell me how to calculate stroke volume is written on the whiteboard. How much blood the heart pumps? It's not a number. It's not a number, it's an expression. So I came in with $10 and I left with 4. What is the volume that heart starts the ejection phase with? Not a number. It's an acronym on the whiteboard. What is this volume? What is this volume? What is this volume? It's end diastolic volume. Can you see that? Does that make sense? That's end diastolic volume. That's how much blood you have in the ventricle before it starts ejecting. Do I make sense? How much blood do you have left after the contraction is complete? It's called end systolic volume. Does that make sense? At the end of the systole. Are you following me? So stroke volume will be what? Using these two parameters, express. Tell me. Okay. Absolutely. Yes. This is a stroke volume. End diastolic volume minus end systolic volume. Are we clear? Why? Why I pay so much attention to that really, really simple statement? Look, if you have a really strong heart, like really, really strong heart, and it squeezes blood super efficiently, making ESV super small, your stroke volume will be higher than in other average form. Does that make sense? On the other hand, if your heart suffered multiple myocardial infarctions and huge parts of your heart are basically like dead, right? It cannot squeeze that well, so your ESV and systolic volume will be really big, right? And your stroke volume will be small. Does that make sense to you? Another example, which I'm kind of jumping ahead of the train, but can you change the amount of blood that goes into the heart? Can you change EDV? Surprisingly, the answer is yes. Because think of it this way. When blood returns to the heart, it returns through the veins. You follow me? Now, especially from the lower limbs, it's really a struggle because blood goes against the gravity. Okay, so it's challenging to return it back. Now, imagine that you are exercising, whatever it is, jogging, lifting, doesn't matter. When you're exercising, your muscles contract. Make sense? Now, when your muscle shortens, how does it change the volume of the muscle? That's muscle. My palms are the muscle. They shorten. What happens to the kind of volume, the diameter? It becomes thicker. Yes. That makes sense? So when you have muscles contracting and bulking out, veins that are trapped between the muscles, they get squeezed. Are you following? Just like you squeeze the tube with the toothpaste, and that pushes the blood to move faster towards the heart through the veins. This is called a muscular pump. Does that make sense? So in a given moment, the venous return, the amount of blood that goes back from the veins into the atrium, increases. Your venous return increases, your end diastolic volume increases, your stroke volume will increase. Does that make sense or not? Now, since you now understand what I mean when I say express, I'm going to explain what is cardiac output. So cardiac output here is the amount of blood that your heart pumps into either circuit in 1 minute. Does that make sense? Yes, it's the amount of blood that your heart pumps into either circuit in 1 minute. Okay? Now, I promise that the question that I'm going to ask now, is simple. It isn't trivial. It is simple. So you understand now what I mean by expression. So how can you express cardiac output? A hint, one of the parameters isn't written on the whiteboard, one is. So how can you find the amount of blood that your heart pumps in 1 minute? How much blood? What is the term, the amount of blood that your heart pumps with each beat? Yes. So how can you express cardiac output with a stroke volume? What do you need to do? If your heart pumps a certain amount of blood with each beat, how do you find how much blood it pumps in 1 minute? What do we call beats per minute? What's the term for beats per minute? Yeah. You need to multiply stroke volume by heart rate. That's it. That make sense? Now, here's the question. You are chilling right there. No offense, like, you're not like jumping around. So your cardiac output is basically at the basal level. That makes sense? Now imagine that you go outside and start jogging, I don't know, playing soccer, whatever. How is it going to change your cardiac output? Huh? Yes, it's going to go up, of course, because, you need more oxygen and nutrients delivered to various tissues and organs. That makes sense? How can you increase cardiac output? Can you increase the heart rate? Sure. Can you increase stroke volume? Sure. Does that make sense? When we talk about cardiac output, when we're going to talk about regulation of cardiac output, you need to keep in mind, okay, what we can manipulate. Does that make sense? What we can change. So basically, your kind of final equation. Put it back here. So cardiac output can be expressed as heart rate multiplied by end diastolic volume minus end systolic volume. Okay? Does that make sense? I basically replaced stroke volume by this expression. So, one more thing. So let's consider you are the baseline. Okay? And yes, you are. It's going to be sort of a weird question, but can you think of any scenario when you need to reduce cardiac output below the baseline? It's not a trick question. It's not a rhetorical question. It is baseline, like lower than that. Can you think of anything that's lower than you sleep? I personally cannot. I don't. When we sleep, right, our cardiac output is at like normal low. If you go below that, you're gonna die, or you're gonna faint, right? So physiologically, for a healthy person, there should be a reserve to increase cardiac output. Does that make sense? Okay, when we exercise, when we're active and stuff like that. So how can we increase it? Increase the heart rate, or increase end-diastolic volume, or decrease end-systolic volume. Makes sense, right? Now imagine the situation. I'm going to give a slightly different spin on that. Imagine we're talking about a patient with the heart that suffered multiple myocardial infarctions. So the ability to squeeze the blood out, so-called contractility, is low. Does that make sense? So if heart doesn't squeeze that well, which of these three parameters is going to fail? If it doesn't squeeze well during injection. ES3, yes. So end systolic volume is going to be higher, right? Does that make sense? If it doesn't squeeze well. If end systolic volume becomes higher, the stroke volume becomes smaller. How can heart compensate? Increase heart rate. Does that make, because to keep up. We're good? Which brings us to an interesting situation, an interesting disease which I would like really to talk about. It's just so, it's the congestive heart failure. So what is congestive heart failure? Let me clarify. So imagine this. You've got a heart right here, okay? You've got two circuits, the pulmonary circuit and blood pumped into the pulmonary circuit by the right side, right? And you have systemic circuit and left side pumps the blood. Are you with me? Good. Imagine that the owner of this heart suffered multiple myocardial infarctions, okay? And let's say these myocardial infarctions affected the left ventricle, okay? So left ventricle isn't as strong as it used to be. It cannot pump as efficiently as it used to pump. Are you following? So the flow of the blood through the systemic circuit becomes lower than the flow of the blood through the pulmonary circuit. But remember, the volumes in a healthy person are exactly the same. But if the left side starts to pump weaker, that's not super easy question, and it's not trivial question. If one side pumps worse than another, what's going to happen to the side that is still normal in function? What's going to happen to the blood volumes? Let's put it this way. If your systemic circuit is weak, what's going to happen to the blood volumes in both circuits? Again, where? Your systemic circuit left side is weak. Systemic circuit blood doesn't go with the same rate. So yes, volumes are going to change. How? It's not a trivial, it's not a simple question. Not regurgitation, but you're on the right track. It's going to be congestion. Does that make sense? So blood, since it is not moving at the same speed through the systemic circuit, will be accumulating in the pulmonary. Do I make sense? So if it's a left side failure, you're going to experience pulmonary congestion. Does that make sense? Now, remember we were talking about pulmonary circuit and systemic circuit and how they are different. Which one has a higher resistance and higher pressure? Yeah, so which circuit has higher resistance and higher pressure? Yes. So pulmonary circuit is generally a low pressure circuit. It's kind of a more, it doesn't have to withstand high pressure. And suddenly, blood starts to accumulate in the pulmonary circuit, which leads to pulmonary congestion and pulmonary hypertension. So suddenly, the blood pressure in the pulmonary circuit rises. And remember, those pulmonary blood vessels, they're pretty fragile. Does that make sense? I mean, they're not used to that pressure. Good? So when you have, imagine that you have a pipe or a hose that is good for certain pressure, and suddenly the pressure in that pipe or a hose starts to rise. What's going to happen to that pipe or hose? Not burst, but I was looking for nothing's going to burst, but leaking, yeah. And those are pulmonary vessels. So where is it going to leak? It's going to leak in your lungs. Does that make sense? So you have pulmonary congestion, hypertension, and pulmonary edema. Good? Now, if your right side fails, which is rare, you're going to have systemic congestion, systemic hypertension, and peripheral edema. There's going to be all kinds of problems like portal hypertension and liver failure. Okay. Now, why? So, that's kind of a really, really far-fetched question. But which failure is more common? Left side or right side? Yeah. Left side failure is more common because usually what happens, think of it this way. Imagine that I am a patient with hypertension, just hypertension because I eat shitty food, I do not exercise, I'm obese, all that kind of, everything's bad, okay? That makes sense. So I have a hypertension. Therefore, my heart, the left side, has to pump against a lot of resistance. Are you following? Does that make sense? Now, if you have to work harder than normal, what happens to your muscles when you work hard? They grow. Does that make sense? So imagine that your left ventricle here, in order to push the blood through, has to grow. It will become, walls will become thicker and thicker at the expense of the chamber. Does that make sense? So you end up with a very small capacity of the left ventricle. Your stroke volume decreases. It has to work progressively harder, but eventually just cannot. Like, there's a limit. Does that make sense? So eventually your left side fails to pump properly, and you end up with it. It's not curable. I mean, except for the heart transplant. Okay, does that make sense? Right side failure. It's much less frequent because basically you got to have a right side cardiomyopathy. And here's the deal: there is a condition known as idiopathic pulmonary hypertension. When people develop abnormally high blood pressure in the pulmonary circuit, so right side has to work much harder. Does that make sense? Now, here's the deal. You know what word idiopathic means? That's good to know for you to go to the medical profession. Idiopathic means we have no idea what causes it. So idiopathic pulmonary hypertension means we have no freaking idea what causes hypertension. Okay? If a person develops idiopathic pulmonary hypertension, the person dies in a year or two. So at this point, congestive heart failure is kind of a secondary problem. Does that make sense? Any questions? I'm trying to find a good analogy. So I'm going to say something. If it clears up, then good. If it doesn't, I'll try to find a better explanation. But when the right side fails, it means that blood moves through pulmonary circuit slower than normal, which means blood gets congested in the systemic circuit. It didn't clear the situation, did it? No. Okay, I expected that. So I hope that this analogy will work. Let me try it. So you have okay, so that's systemic. Okay, that is pulmonary circuit. Okay, it doesn't matter either way is fine, because if you understand it one way, then you can just flip it now. So imagine that those are not circuits, like circulatory circuits, but roads, the bus routes. Okay, and you're supposed to have 5 buses in each at any given moment. Does that make sense? And buses take the H shape overall route. So 5 buses here. Okay, and 5 buses here. That shows the equivalent volume. Do you understand it? Not sure? Be honest, please. Don't like shut the fuck up. Just move on. So again, this is the bus route. Okay, and for some reason, at any given moment, on the green loop and on the blue loop, you can have 5 buses only. They should be equivalent. Does that make sense? But that's a continuous, so they go like in this direction. Okay. That makes sense? Now imagine that for some reason there's a traffic jam in the blue. So the buses move slow. Okay? So some buses that are supposed to return from the green loop, they can't enter because the maximum, like they can't enter, the capacity is full. There's just not enough time. So you have extra buses being stuck in the green loop because buses in the blue loop are still moving. When one bus leaves, another has to enter. Okay? But since they're moving too slow, it doesn't leave. No, that was a bad analogy. I'm trying to think. Okay, let me try and do numbers. Okay, that may actually help since we've got cardiac output stored. Okay, so pulmonary circuit. Cardiac output equivalent to 5 liters per minute. Are you following me? Systemic circuit. Cardiac output equivalent 5 liters per minute. Does that make sense? Now, why? Because both sides of the heart, they work synchronously. They pump, they have the same volume of blood in each circuit. And they have to pump that volume through the circuit in 1 minute. That's the definition of cardiac output. Are you following? Now, imagine for a second that we have a problem. Which side do you want to fail? The right side, which means if right side fails, is it going to pump more or less in a minute? Less. So pulmonary cardiac output is now 4 liters per minute. Now you have only 4 liters in that circuit. You can't drop that blood anywhere. Like you're not bleeding it out. So if it's not in the pulmonary, where it's gonna be stuck. So in the systemic circuit, technically, the output should be 6 liters per minute. Did that clarify the situation for you? It's the H-shaped continuous circle. So how about that? We're going to talk, okay? Just want to ask